My name is Tehran Erdogan. I'm the president of Plymouth Grating Laboratory. We're located just outside of Boston in Massachusetts in the United States. And today we're going to be talking to you about how to choose the right diffraction grating for pulse compression. Many people who don't know optics super well ask me what I do or what our company does, and I try to explain that pretty much we put lines in pieces of glass, and so at a very simple level, that's all we do. But I have to say that probably one of the most exciting parts of my job and our job as a company is coming up with solutions that are truly useful to people. And our customers really are laser builders and laser manufacturers for the most part. And so what we try to do is make the best possible components we can to enable you to make the best possible laser you can. And so what we're going to be talking about today is how to help you maybe better understand some of the gratings that we manufacture and how they can be useful to you, and how you can go about zeroing in on the best possible solution for gratings that you need for your laser system. Okay, so just for starters, a word about diffraction gratings. That is what we do. So diffraction grating is really nothing more than some sort of periodic variation of some optical property, such as index of refraction or the surface profile on a substrate. And when that variation is comparable to the wavelength of light, when you shine light on that grating, you find that not only is some of the light reflected, as we always anticipate with what's called specular reflection, but we also find light goes off into different directions, and the light that goes in those different directions gets separated into different colors, each of which travels in a different angular direction. This is so-called angular dispersion, and that's really what makes gratings useful. Most gratings are used for spectroscopy, but today we're going to be talking specifically about gratings used for laser applications, which is what we specialize in. Just briefly, the outline of the talk today, we'll start by saying a few words about some laser grating applications. We'll take a closer look at what gratings look like on a macroscopic and microscopic scale. We'll talk about, just very briefly, about how we manufacture gratings using our technique called scanning beam interference lithography. And then I'll spend a little bit of time on some basic optics of gratings, because I think it's important to understand those to help you choose the best grating for your application. And the last part of the talk, which is kind of the highlight, is we're going to help you through the decision process of choosing the right pulse compression gratings for your laser. Okay, so again, starting with just very briefly some laser grating applications. So this chart just shows 4 of the primary applications that we at Plymouth Grating address. I'm going to say more in a minute about pulse compression, but this is by far the largest application for the gratings that we manufacture. Perhaps our fastest growing application is spectral beam combining. And the idea here is that one can take an array of either typically diode or fiber lasers, each of which is at a slightly different wavelength, and combine them using the angular dispersion property of gratings so that the light gets incoherently combined into a single beam. This is a method of power scaling, particularly for very high power CW laser applications like directed energy or industrial laser beam applications. Another area that we address is laser steering and focusing. This little cartoon at the bottom left here shows the diagram at the end of the 176 beam lines of the LMJ laser at the CEA Center for Atomic Energy in France. And we actually manufacture gratings that are used to steer the light into the frequency tripling crystal combination, these KDP crystals. And then we make focusing gratings that take the ultraviolet light coming out of those crystals and focus it down onto the target. So gratings can actually be used in this case like a lens type application. And lastly, one of the areas that we address is laser-based metrology systems, where gratings are used essentially as a very high precision encoder in place of displacement measuring interferometry. We're not really going to talk about these 3 applications today. We're going to focus on pulse compression. Now, the industries that take advantage of these applications primarily scientific research, medical, industrial, and defense. So for example, short pulse, very high intensity short pulse lasers are used for a lot of different scientific research applications, but they're also used in medical and industrial applications. Industrially, especially for very, very short pulse femtosecond type machining applications. Spectral beam combining is also used for high power CW industrial applications and for directed energy and defense. Laser steering and focusing, I showed you, this is the target chamber of the LMJ laser in France, where there are 176 beams coming into the target here. But another interesting application is gratings can be used to cylindrically focus laser beams for applications like annealing in the semicon industry. And for metrology, probably the biggest customer there is wafer steppers, and some machining applications do take advantage of grating-based metrology systems as well. Okay, I said we were going to focus on chirped pulse amplification, so let's take a minute to look at the passage of light through a CPA or chirped pulse amplification laser. Though many of you are familiar with this, I figure some of you might not be, so it's worth taking just a minute to do that. The idea is, if I have a very, very short pulse, which could be anywhere from femtoseconds to picoseconds, and we want to amplify that pulse, we could be limited by either saturation or damage considerations in the amplifier. So what can we do about that? Well, one thing we can do is we can chirp that pulse using what's called a stretcher. This is a classic, what's called Martinez stretcher. There's a pair of gratings and a pair of lenses and a mirror here. And what happens is, because of angular dispersion, the red light, or the longer wavelength light, travels a shorter path distance than the blue light, or the shorter wavelength light. And so when the pulse emerges from this stretcher, it gets stretched out in time with the red frequencies leading the blue frequencies. What that also does is it decreases the peak instantaneous pulse intensity. And that allows you to amplify it to a much larger energy, because the peak intensity is lower. So we can now get this very large amplified stretched pulse coming out of here. And if we now go back through another set of gratings, in this case, I'm showing a classic 4-grating compressor, where the gratings are arranged so that now the red light, which is the longer wavelengths, travels a further distance than the blue light, which is the shorter wavelengths, so that the blue light gets to catch up with the red light, and we get a single, very intense, amplified short pulse coming out of this laser. So this is the technique of chirped pulse amplification. It was actually developed in the 1980s. The basic idea was taken from radar, but it was first implemented in the 1980s by Gerard Moreau and Donna Strickland at the University of Rochester. And they recently were awarded the Nobel Prize. And for those of you who are not, again, familiar, many of you are, I'm sure, but perhaps the single greatest graphical illustration of why this work was worthy of a Nobel Prize is a plot of peak laser intensity versus time. And you can see that people were struggling to get past sort of the 10 to the 14, 10 to the 15 watts per square centimeter range until CPA was introduced, in which case suddenly the ability to break that barrier and get up into sort of relativistic optics and into much, much higher intensities became possible. So let's take a closer look at some different types of pulse compression gratings. Here's a chart of the 4 major types of gratings that we manufacture here at PGL. So multi-layer dielectric gratings tend to be sort of semi-transparent looking, like this one. Here's a large gold grating, one of the largest ones we've made. And you can see it looks like a big flat gold mirror, basically, except that you can see diffraction effects. This is a fairly large transmission grating. And here is a newer type of grating we call hybrid gratings. Now, if we look more closely under a scanning electron microscope, you can start to see what's different about each of these different grating types. For example, the multi-layer dielectric grating has a nicely etched grating pattern in glass, and it sits on top of a thin film coating. In this micrograph, you can see the first 5 layers of the thin film coating. In fact, there are many more layers below this. A gold grating is typically a gold coating on top of another grating etched in glass, although you can see the grating is much shallower than the MLD grating. transmission gratings are very deep, but they're very simply grooves etched directly into a glass substrate as shown here. And the hybrid grating is a hybrid between the gold and the multi-layer dielectric. It's basically a dielectric grating sitting on top of a gold coating. And perhaps it's a little clearer to see all that in these cartoon images. So here's an MLD grating. We have an etched grating in glass sitting on top of a thin film coating. This is basically a high reflecting mirror. For a gold grating, we have a gold conformal coating on top of a shallow glass grating. For hybrid grating, we have dielectric etched grating on top of a gold layer like this. And for transmission grating, we're simply etching a fairly deep pattern of grooves directly into a glass substrate as shown at the bottom here. Now, what differentiates pulse compression gratings from other types of gratings, especially those that would be used, for example, in spectroscopy? Well, the things that pulse compression gratings care about most when used in laser applications are first and foremost diffraction efficiency. For almost every laser application, it's desirable to get as close to 100% diffraction efficiency into a single order as possible. And so we work very hard on trying to get these high diffraction efficiency gratings. Diffracted wavefront error is another critical feature. Not only do the substrates have to have very high quality, but the grating lines themselves have to be very perfect and free from defects to ensure that the wavefront coming off the grating is very high purity. Laser damage threshold is quite critical because these are going to be used at the end of an ultra intense laser system. And uniformity over very large areas sort of underpins all of these. All of these features, we'd like to have very good uniformity over quite large areas compared to other optical systems. Okay, let's take just a minute to say, how do we make these gratings? And in particular, how does one achieve the features that I just showed you on the previous slide? And I'm not going to go into all of the process steps, but perhaps one of the most critical process steps, which is kind of at the heart of what we do, is the patterning of the gratings themselves, the formation of the grating lines. And we use a tool at PGL called the nano ruler. And this is a hybrid of a ruling engine, which was developed, many years ago for writing gratings simply by mechanically etching grooves into a soft surface, typically a metal, and holographic gratings, which are made by interfering two beams of light to create a fringe pattern that gets exposed in a photoresist. And we do this by creating an optical system here, which forms two interfering beams of light at a point on top of a large substrate here. So this is a nearly 1 meter substrate. And the substrate sits on a carriage. You can see down below, this purple carriage here is the one that you see here, is on an air-bearing stage on a very flat vibration isolated table. And we move the substrate back and forth in the X and Y directions underneath this beam that's formed by the optical system above, and thereby cover the entire surface of the grating with this fringe pattern that's formed by these two interfering beams. Now, how does that work? How do we maintain coherence of those fringes over the whole grating surface? Well, here's a little set of cartoons that tries to explain that a little bit more clearly. So this is sort of a side view of what I just showed on the previous slide. So here's the grating substrate. There's an XY stage that's whose position is controlled and measured by an interferometer. And then there's a little holographic grating writing set up here, which creates the interference of two beams right on top of the substrate. Now, the key to all of this is something that we call fringe locking. So fringe locking basically means that we lock the position of the fringes that are formed by the interference of these two beams to the surface of the substrate. So as we move the substrate back and forth, and we know its position extremely accurately because of the interferometry that's being done, we also adjust the phase of one of the arms of this interferometer to cause the fringes to move in lockstep with the surface of the substrate continuously. And so that's called fringe locking. Once you've set up that feedback loop to do that, then it's merely a matter of raster scanning the substrate under the interfering beams, and you can sort of paint that fringe pattern onto the exposure material, which is typically some kind of photoresist. We have several different methods. Sometimes we write in what we call the parallel mode, which means we scan back and forth along the grating fringes. Sometimes we write in what's called the Doppler scanning mode, which means we scan back and forth perpendicular to the fringes. And in principle, you could scan in an arbitrary direction as well. Now, all of that is good, except how do we maintain uniformity? The key to that is averaging. So we actually make these scans overlap quite significantly so that the final exposure pattern is very uniform. So this combination of fringe locking and averaging is what allows us to make very large, essentially arbitrarily scalable size gratings in a simple fashion. Okay, so I want to switch gears now and talk a little bit about some basic optics of gratings, which I think will be helpful to understand the decision process. Let's start with the most basic feature of gratings, which is what's called diffracted orders. And those are described by something called the grating equation, which is shown down here at the bottom. So here's a cartoon of a grating. Light is incident on the grating at some angle indicated by these green rays, and it's diffracted at some other angle indicated by these blue rays. Now, in certain special directions, what we find is that there's constructive interference between the beams coming in and the beams going out on successive periods of the grating, and those constructive interference directions correspond to what are called orders. And the grating equation is simply a way of writing down that there should be an integer number of wavelengths between contained in the difference between this path length AB and this path length A prime B prime. So you can see I have 1.5 wavelengths here and a half a wavelength here. So the difference between those two is exactly 1 wavelength. And so this is what's called the first order diffraction. It's the direction in which there's exactly 1 wavelength of difference between light diffracted off 2 successive periods of the grating. Okay, what about diffraction efficiency? How much light goes into each of those orders? Here I'm showing an example where light is incident at 10 degrees on a grating of a certain period, and there are 4 different diffracted orders. There's the 0th order, which is the specular reflection, and then there's the +1, -1, and -2 orders. And I'm just sort of suggesting there might be some distribution of intensities in these different orders. Those are called diffraction efficiencies. And to find out what those are, you really need to model things at the sort of micro scale here using electromagnetic theory. So it actually turns out it's the shape of the grating teeth here that determine how much light goes into each different direction. I have an example over here on the right. This is a gold grating, and I'm showing what the different diffraction efficiencies are into the -1 order for a binary grating, as well as several different types of what are called blazed gratings, or gratings that have asymmetric teeth. Now, the reason for doing this is because it's interesting to illustrate that it turns out blazing doesn't necessarily follow your intuition when you get into the regime where the grating period is comparable to the wavelength of light. You can see that here. There are 3 different blazes that all look like they should give you higher diffraction efficiency because the light is coming in and coming out, reflecting off these teeth. But in fact, it's the binary grating that gives you the best diffraction efficiency. And that's just meant to illustrate that blazing intuition kind of breaks down when you get into the micro scale. I want to say just another word about the grating equation and diffracted orders here. So one of the things that we find very useful is to plot the grating equation on a graph like this, where I'm plotting the angle of incidence on the x-axis here and the angle of diffraction on the y-axis here. So this plot here corresponds to the diagram that I showed you on the previous slide over here. So in this case, I'm actually assuming the light is 633 nanometers, so it's a helium neon laser. It's coming into a grating that has 850 lines per millimeter. And I told you the diagram looks like this. How do we know that? Well, if I plot the grating equation, I find I get this family of curves where there's one curve for each order. So for example, there's this curve here, which is the 0th order. When I come in at, say, 20 degrees, then light gets reflected at 20 degrees. There's a curve for the +1 order, the -1 order, -2, -3, and so on. The example here shows light coming in at 10 degrees, So if I follow the 10-degree point on the x-axis here, I find that the -2 order is diffracted at about -65 degrees, -1 at about -20, +1 at about +10, and excuse me, 0 at +10, and +1 at about 45. And that's what you see over here. So this is a very convenient way to quickly see what the angles of diffraction and potential orders are for a given incident grating, incident angle. Okay. Now, one of the things that's important for pulse compression gratings is we don't want a lot of orders. It turns out that we essentially always are manufacturing what we call single order diffraction gratings. And the reason for that is that we would like to assure as much diffraction efficiency into one order as possible. And when you have a lot of orders competing for that light, it's hard to do that. So one way to see that is a plot here. This is the ratio of the wavelength to the period of the grating, something that I'm going to say more about in a few minutes. The wavelength to period ratio as a function of the angle of incidence. And what you can see is that when the wavelength to period ratio is high, this red region here and above, there's no diffraction at all. As I start making it smaller, in other words, as I start making the grating period larger, I find that there's this m equals -1 cutoff curve here. So all of the combinations below this curve give me some diffraction. But as I keep making the period larger and larger, or this ratio smaller and smaller, I start getting these cutoff lines for higher orders. So here's the m equals -2 line, m equals +1, +2, and so on. So down in this region down here, I have lots of orders. This yellow region in the middle here is the region where I have exactly only m equals -1 diffraction. So that's generally where we're always operating with the gratings we manufacture. So that means that the wavelength to period ratio is generally always between about 0.7 and 2. We're somewhere in this yellow region here. And just by way of example, the example I showed you in the previous slide, I had a 633 nanometer laser with an 850 lines per millimeter grating, means that the wavelength to period ratio is 0.54, which is here, which you can see is below not only the m equals -1 cutoff line, but it's also below the +1 and the -2 cutoffs. So I have all of those orders present. That's why we saw all three of those grating orders. Okay, so that's one property about gratings. The other property I just want to take a minute to explain is dispersion. So one of the most significant ways that gratings are used in pulse compression is to provide what's called temporal dispersion. And the basic concept can be illustrated with just two gratings. If I take two gratings and I arrange them parallel to one another like this, and I send light into one of the gratings, different wavelengths will be diffracted at different angles. And after diffraction off the second grating, they'll come out parallel. So I'll get the laser beam, in this case, continuing on. But the red or longer wavelengths will have experienced a longer time delay than the blue or shorter wavelengths. So this is called temporal dispersion. And one can show that the temporal dispersion, or the change in delay time for a given change in wavelength, is proportional to the order squared, it's proportional to the wavelength, it's proportional to the grating frequency squared, and it's proportional to this distance between the gratings. So the further apart I make those gratings, the greater the temporal dispersion. And you can see it also depends on angle. Usually this is given in picoseconds per nanometer. Okay, and we can make plots of that, which is sort of a more convenient way to look at it. So here's an example. At 800 nanometers, I have three different gratings here shown: an 1800 lines per millimeter grating, a 1480 lines per millimeter grating, a 1200 lines per millimeter grating. And on this axis, I'm plotting the temporal dispersion or d tau d lambda in picoseconds per nanometer. And I'm also dividing that by the distance between the gratings. So in other words, you can think of this as how much temporal dispersion is there for gratings separated by 1 meter. If you make them closer or further apart, then this number just goes up or down. So as an example, if I come in at 40 degrees on a 1480 lines per millimeter grating, I get 10 picoseconds per nanometer of dispersion for every 1 meter of separation of the gratings, as shown in this little cartoon in the lower right here. Okay, now, one of the useful things I think you'll find on our website is we actually have a tool where you can play around with those numbers yourself. And I'm going to, let's see, briefly give you a demonstration of that. So this is our website. And if you go to this guidance tab here, we have something called the grating calculator. And I can, so for example, put in a 1480 lines per millimeter grating. I'll do the example I just showed you at 800 nanometers and hit plot graph. And it shows you the angle of diffraction versus the angle of incidence. So for example, if I came in at 40 degrees, I would get diffraction at about minus 32 degrees. I can also plot angular dispersion directly. So this tells me how many degrees per nanometer of dispersion, or even temporal dispersion. So this is the picoseconds per nanometer per meter of separation as a function of angle of incidence, again, for 1480, 800. I can also plot that in picoseconds squared, which is another way of describing temporal dispersion. And let's come back here, and let's say I come in at an angle of 50 degrees. And I can also do things like see how things depend on wavelength. So I'm going to look at between 700 and 900 nanometers at 50 degrees. And I'm going to make this guy go to -5. So this is how many picoseconds squared, or if I want to do this in picoseconds per nanometer, I can do that since that's what we've been talking about. This is how many picoseconds per nanometer of dispersion I get at different wavelengths. And that's an important thing to remember, that usually people specify a certain number of picoseconds per nanometer, but that's only at the central wavelength. It actually varies as a function of wavelength. So hopefully you'll find this tool useful if you want to kind of play around with the specifications of gratings. Okay, I want to jump to the last and sort of highlight topic of the talk. So how do you go about choosing the right pulse compression grating for your chirped pulse amplification laser system? Well, I tried to put together a little, what I call decision table here. It's not perfect, but it gives you a sense. Usually the starting point is knowing the wavelength that you're interested in. So what wavelength is your laser operating? And the reason for that is properties like absorption, reflection, and transmission dictate what materials are possible for that wavelength, and that dictates which grating type is possible. So for example, on this simple chart here, I'm just showing that different grating types, for example, MLD and transmission gratings, are all dielectric. So we're going to make those with standard oxide dielectric materials, and those can be good down to ultraviolet wavelengths and maybe up to about 2 microns or so. But beyond that, they're not very good in the infrared. So sometimes people come and say, hey, can you make a grating at 3.5 microns? That's an MLD grating. In principle, it's possible, but we don't have material systems to make those, so not today. Gold, on the other hand, operates very well from the mid-visible all the way into the far infrared. So we can make gold gratings even out to 10 microns and beyond. And some people are using those in, for example, optical parametric chirped pulse amplification systems. Hybrid gratings are basically the intersection between those two. So those work well from the mid-visible out to, again, about 2 microns or something like that. Okay, so that's a starting point. Usually the next consideration has to do with damage. And so we ask people, what is the amplified compressed pulse energy coming out at the end of your laser, and what is the pulse width? So if you know those two things, you know how damage and size of the grating are going to factor into things. So for example, here is a simple chart just to give you a sense. This is not an exact chart because damage does depend on a lot of different things, but just to give you a sense for how damage varies with different grating types, you can see that this is damage in joules per centimeter squared, and this is pulse width. So for long pulses, that's tens of picoseconds out to nanoseconds, dielectric gratings tend to have joules per square centimeter of damage threshold. Gold gratings are much more like, almost like an order of magnitude smaller than that. So they tend to be more like 100, 200 millijoules per square centimeter. As the pulse widths get shorter and shorter, Gold gratings don't tend to change very much. So they actually can have hundreds of millijoules per square centimeter damage, even down to tens of femtoseconds of pulses. However, the dielectric gratings, because of the change in the physics involved in the damage mechanism, start to see a significant decrease in damage threshold, so that by the time you get down to several tens of femtoseconds, dielectric gratings seem to have a comparable damage threshold to that of gold. Hybrid gratings we don't know as much about, but we know they're comparable to gold down in this regime, and up here we don't really even have any measurement data. But I'm here just sort of assuming they're no better than, but they might be better than gold up here. Okay, so that's damage threshold itself. What about size? When you have very high pulse energies, it could be that the size of the grating ultimately is the limiting factor in the pulse energy you'll be able to achieve coming out of your compressor. So for that reason, people often ask, what's the largest grating size I can make? And because many of our processes are shared for our different grating types, it turns out that for MLD, gold, and hybrid gratings, they're all about the same. We can make gratings almost up to 1 meter in length and in width about 600 and some millimeters. Transmission gratings are a little bit limited by the etch processes we use to get these deep etches. And so those tend to be limited more like about 0.5 meter in size. But this is today's kind of upper limits. I will point out that people are always interested in pushing these to higher values, and that is something that we are investigating. And in the not too distant future, it's possible we will be able to go further than this, but this is where we're at today. Okay, so we've talked about wavelength, damage, and size. What about dispersion? It turns out that usually the limiting factor here is the maximum amplifier intensity that the system can sustain, which determines how much the pulse should be stretched, which of course tells you how much dispersion you need to stretch and therefore recompress that pulse. I'm not going to spend a lot of time on it, but I'll just say one of the quickest and easiest ways to get an idea for that is to sort of use this universal chart. This is a plot of something we call the temporal dispersion factor as a function of, here's that wavelength to grating period ratio again. So this is the ratio of the wavelength to the grating period, or it's the product of the wavelength to the grating frequency. Each unique wavelength grating period ratio has a corresponding litro angle to the grating, or the angle at which the light is retroreflected in the minus first order. And this quantity, delta, the temporal dispersion factor, is simply something that you multiply the separation of the gratings by, and you divide by the wavelength, and that gives you the temporal dispersion, d tau d lambda. So if you know your possible grating separations and the wavelength, this sort of gives you a nice, quick and dirty way to see how much dispersion you'll get from different grating frequencies. So for example, I mentioned previously, a 1480 lines per millimeter grating at 800 nanometers has a wavelength to period ratio of about 1.2. And at the litro angle, that tells me that I get about 20 picoseconds per millimeter of this dispersion factor, and I can multiply that by the distance between the gratings. So for example, if the gratings are a meter apart or 100 millimeters, that would mean I'd get 100 picoseconds per nanometer. And then I have to divide by the wavelength in nanometers, and it turns out I get about 10 picoseconds per nanometer for that combination. The other curves on here just show you that that's at the litro angle. If I vary in angle, I can actually tune the dispersion that way as well. So one thing I can tune is the separation between the gratings here. The other thing I can tune is the angle of incidence, and that changes the dispersion. So these just give you sort of a sense for how much the dispersion changes. And the last thing I'm going to say about this is you'll often hear people say high dispersion gratings, low dispersion gratings, and that simply is another way of saying high frequency, low frequency, or short period, long period gratings, because you can see there's a monotonic relationship between the grating frequency and the dispersion. So the higher the grating frequency, the higher the dispersion. So that's why those terms are sometimes used interchangeably. Okay, lastly, there are all sorts of other system requirements, such as loss budget, pulse width, the geometry of your system, that can drive which grating type and which specifications are most desirable. So we've tried to put together a simple guide. Well, after you see it, you might not say it's so simple, but we'll see. to help you through that process. So here's an example. I'm starting. Now I'm plotting this wavelength to period ratio on the vertical axis. And you can see why we like to do that, because different people have different lasers at different wavelengths. So this is a sort of more universal way of capturing what's the ratio of that wavelength to the grating period, or the product of the wavelength and the grating frequency. And what we're showing here is that the diffraction efficiency for an MLD grating can be quite high, in fact, in the very high 90% range, over all of these different wavelength to grating period ratio combinations for S polarization, and these combinations for P polarization. So this gives you a sense for where you can achieve high diffraction efficiency. Now, the same can be done for other types of gratings. Here's gold, hybrid, and transmission. And you can see that we never get quite as high diffraction efficiency from a gold grating, simply because the gold absorbs several percent, up to even 5% of the light. Hybrid gratings can achieve very high diffraction efficiency, but only for this narrower range of wavelength to period ratio. Transmission gratings are sort of somewhere in between. They can't get quite as high as MLD gratings, but they can get higher than gold gratings. And the reason for those limitations are now shown with these annotations. So what happens is, if I try to make a P polarization transmission grating with a higher wavelength period ratio, the grooves simply become too deep to manufacture. All of these get cut off at the top here because there's no diffraction for a wavelength period ratio above 2. And at the bottom, they get cut off because, as I said previously, higher orders show up when the wavelength period ratio is too small, so you can't get high diffraction efficiency. There's something else interesting that happens with MLD gratings. We get something called guided mode resonances, and there's a range in which those are a problem. I'm not going to go into the details here. We don't have time, but love to chat about those for anybody who's interested. And you can also see here that both MLD gratings and transmission gratings have the possibility of being non-polarizing or operating simultaneously in both S and P polarizations. There are no good solutions or practical solutions for gold and MLD gratings that are non-polarizing. Now, that's just one quality. Another one is spectral bandwidth. So down at the bottom here, there's a key. A solid green means very wide spectral bandwidth, tens of percent of the wavelength. And then the cross-hatched means about 10%, and the single-hatched means a few percent. So for all four of those grating types, you can also see what can be achieved in terms of spectral bandwidth at different wavelength to period ratios. And you can see that the gold and hybrid gratings are really the winners here. They can achieve very broad spectral bandwidths. MLD gratings never quite achieve that broad of a spectral bandwidth. Transmission gratings in S-pole, about the same as MLD. In P-pole, they can actually be fairly broad in spectral bandwidth. And lastly, angular bandwidth. So this is quite important for geometrical considerations in designing a compressor. Depending on what the size of the beam is and how much dispersion is required, you might need a very high angle of incidence deviation between the incident light and the diffracted light. And that is easy to do when you have a very broad angular bandwidth, which is possible with gold and hybrid gratings. It's difficult to do with MLD gratings, except at this very special range here where the wavelength to period ratio is about 1.8. This corresponds to a litro angle of about 65 degrees. And transmission gratings, the angular bandwidth is not so broad, but it doesn't really matter because the light transmits through the other side of the grating, so you don't have to worry about the two beams overlapping. So this chart, this guide that we've created, is sort of a quick and dirty way to sit down and say, I know I need very high diffraction efficiency and very broad spectral bandwidth. I don't care that much about angular bandwidth. And you can sort of see what ranges of grating frequencies are possible for your wavelength of the different grating types here. And this is sort of a simple way to guide you through that thought process. Okay, so just in conclusion, there are a number of different types of pulse compression gratings. As we talked about, MLD, gold, or metal, hybrid, metal-dielectric, and transmission. And choosing the best one really requires you to know as much as you can about your system. We recommend starting with wavelength, damage, and dispersion, and then look at things like diffraction efficiency and bandwidth. But hopefully these guides that we put together will be helpful in walking you through that process. I have some contact information here at the bottom. And the last thing I just want to say is that I realize those charts are very busy, or there's a lot going on there. So I do want to say that much of the content of this presentation you can find in the technical notes on our website. There's a URL here. If you go to plymouthgrating.com under guidance and technical notes, you can read more about those charts that I showed you. So with that, I'm going to end the formal part of the talk, and I'm going to open it up to questions. I would be more than happy to answer questions. I see I've got a number of them here already, and I'll start with those, but please feel free to add to the list of questions. So thank you very much.